last topic to do, which is the method of substitution. Okay, so as an example of this, let me revisit a problem that we did last time. Okay, so we wanted to find an antiderivative of e to the 2x. Good? Now, how did we do it? We guessed, right? And we said, oh, let me just try e to the 2x. And then we said, let's check what's the derivative of e to the 2x. It's 2e to the 2x, which is not equal to what we started with of e to the 2x. Okay, so then we made a second guess of, let's say that it's 1/2 e to the 2x. Check. What's the derivative of 1/2 e to the 2x? 1/2 times e to the 2x times 2, and that equals e to the 2x, which is there. It worked. Oui ou non? Okay, so we guessed, we checked, right? Wasn't that hard to reverse engineer it, but did require a minor bit of work. Yeah. Okay, so let's do this sort of a different way. That while, okay, so the technique I'm about to show you is not necessary per se here, because was it that hard to realize that we needed to have that 1/2 there? No, okay. But it's maybe a good way to sort of illustrate the beginnings of the technique of substitution. Okay, so what I'm going to do is let's just return to the original problem. Okay, and wouldn't it be nice if that 2x was just an x? It sure would be, right? And so what I'm going to, but I can't just erase the 2, right? So what I'll do instead is let me call 2x some other quantity. Okay, so that's perfectly good. And then what's the derivative of u? Okay, now, we kind of ran out of time, so we never really talked about differentials, but this du over dx thing, does it sure look like a fraction? Okay, is it actually a fraction? Not really, okay? But there is a sense in which I can kind of pretend that it is and multiply dx by both sides to get this other expression, okay? These things, du or dx by themselves, those are called differentials, okay? And essentially they're just a derivative with a dx or du or d whatever tacked on, okay? Yeah, okay, so let's just leave that on there. Okay, so I took the derivative and I got 2, and then I sort of multiplied this expression so that, like, because look at the thing we started with. We've got a dx there, right? So can I take this expression here and solve it for dx? In this case, that's real easy. It's just du over 2, right? Okay, now what I'm going to do is I'm going to substitute. Well, what did I make equal to u? Okay, and what is dx according to what we just did? Du, but over 2. So this becomes this. Okay, so I just substituted all those things in. Okay, so I'm getting a look of doom from Patrick. Right? Okay, so is that all right? Okay, now, one of the things that's true about integrals is if I have a constant inside, can I take that out? Yes, so I can do this. Mhm. Yeah, good. Okay, so why is it okay for me to pull that 1/2 out front? It's a constant, okay? And like if we think about doing area or antiderivatives, right? Am I going to get the same answer if I wait and deal with the 1/2 at the end versus if I deal with it from the get-go? Yeah, okay. So constants you can move freely outside of the integral sign, okay? And that's nice because look what we've done. We've changed the problem, in a sense, into something that's trivial, okay? What's the antiderivative of e to the u? E to the u, done, okay? Um, and then because we had the half out front still, then, well, the half's got to stay there, okay? And then the last step was, what was u? It was 2x, okay? So I'm going to resubstitute that back in, and there's our answer. Okay, now, not shockingly, it's the same answer as we had a minute ago from the guess and check method, okay? And so in this case, I would not have actually done this trick because I think doing the sort of mental gymnastics of the 1/2 from the guess and check way is simple enough in this case that we can just do that. Okay. Um, but this illustrates what the technique is because not always will it be so obvious what to do. Okay. So does that kind of make sense? Okay. So questions, preguntas, and or fragens. Oh, yeah. Yes. Right. Okay. And why is that the case? Well, what's the derivative of e to the x or e to the u? Yeah. And so if the derivative is the same thing, then the antiderivative will have the same property. Okay. Um, right. So this step right here, um, we have to know our basic derivative rules well enough that we can reverse all of them. Okay. So for example, like let's say that we had secant squared of x here. What's an antiderivative of secant squared of x? Tangent of x, right? How do I know that? Well, it's because I know that the derivative of tangent is secant squared, and therefore the thing works in reverse, right? Okay, so yeah. So essentially, the method of substitution, the goal here is to take something that doesn't look doable and turn it into a problem that's easier, okay? And there's details along the way, right? So it's not like it just magically turns it into an easier problem. There's the art to it, okay? The other thing that's a little tricky sometimes, though here it was pretty easy, is I chose to let u equal 2x, right? What about if I had let u equal to e to the 2x or some other thing, right? Now, in the given problem here, was there really that much option for what we were going to let u equal? No, because the thing we were integrating really only was one simple function, okay? But if the thing that we're integrating is a little nastier, then maybe it's not quite as obvious what u should be, okay? And so there can be a little bit of an art form to correctly choosing u. Okay, now, how do you know if you've picked the wrong u? You know that you've picked the wrong value of u if when you get to, so that step there, when we substituted, are there any x's left over? No, everything now is purely in terms of u, okay? you know that it's that you've messed up and chosen a bad u if when you get to that step, there's still x's there that you can't get rid of. Okay, because that was the whole point of this substitution, was to get rid of x, or 2x, right? And so if there's still x's there, then you probably have messed up. Okay, and I say probably because there is, of course, one interesting other example. Okay, okay, so got it? All right, so let's try another one. So I mentioned last time and the time before that this is a function that there is no antiderivative that you can write down in terms of elementary functions. Okay, but I'm going to throw an x out front. And so I have changed the question, and I claim that we can do this problem. Okay, now, is this at all obvious from the mental gymnastics standpoint? No. Okay, and it's definitely not something that we've previously memorized. So those two options are off the table. And therefore, the only thing left is to try this substitution technique. Okay, so like I said, there's really only three options that you have. It's obvious, slash some slight mental gymnastics, or use substitution. Those are the only techniques that you guys have at your disposal. Okay, now you go into Calc 2, you get a whole bunch of other ones, but that's for another day. All right, so the art form to picking u is you want to pick u so that the derivative of it is something else that you see in the integral. Okay, so what would probably be a good choice for u here? X squared. Okay, and the reason is, what's the derivative of u? Okay, and therefore the differential of u is just 2x dx. Okay, I'll just do that in one step. Okay, is that okay? So can I solve this equation for dx in terms of du? It's du over 2x, right? Okay, so I've got u and I've got dx. Now let me substitute those over to here. What did I say x squared was? U. And then what's dx? Du over 2x. Can I simplify? Because what happens to the x's? They cancel. Okay, so we've gotten to the point, have I chosen the correct u? Yes, because there are no x's left. Okay, does that make sense? Okay, so at this point, it coincidentally looks like the previous problem. And so what's our antiderivative? Okay, and then what was u? That. Okay. Okay, so what we're actually doing here is kind of, it doesn't look like it at first glance, but technically speaking, what we're doing is running the chain rule in reverse. Okay, and by writing it in these terms, like with u and whatnot, it makes the parts easier to see, and it also means that you're not doing everything in one step, right? It's broken down into a series of smaller, easier steps that hopefully each individual one isn't too bad. Okay, so does that make sense? Good? Okay. Um, so let's maybe look at a few other ones here. Okay, any questions on this one? No? Okay. sorry, that's not what I meant to do. Well, okay, let me just remind us. What is this antiderivative? Natural log of, okay. Now, strictly speaking, there need to be absolute values there, although I'm not going to like kill you guys if you don't put it there because it's kind of picky and technical. But it does, it can cause problems if you forget it down the road. Okay. All right. So let's just remind ourselves of that fact. And let's say that we had this instead. Hmm? What? Write x to the minus first? You could. No. Okay, so I claim this isn't obvious. Okay. And if you think it is, write down what you just did. So Mark guessed that it's natural log of x to the minus first, right? What's the derivative of that? That, right? Because it'd be the derivative of something to the negative 1 would be negative 1 times the something to the minus 2 times the derivative of the something. Is this equal to what we started with? No. Okay. So that is not going to help us. Okay. Um, so let me try this substitution technique and see what happens. All right. What should we let u equal? Yeah. Okay. And I will give you a hint here. If I let u equal x, then what does that do? All it does is change the problem from x's to u's, but it doesn't actually change anything. Okay. So letting u equal x, never a good idea. Okay. Okay. So if that's u, what's du? What's the derivative of this? Yeah. So the derivative of log x is 1 over x, and therefore the differential is that just times dx. Okay. And can I solve that equation for dx in terms of du? Sure. What do I get? X times du. Okay, good. So now, um, let's start plugging everything in, doing the substitution. So what do I have? I have dx, which is x times du. I've got the natural log of x, but what did I call the natural log of x? U. And then I have the x that's in the bottom. And what happens to the x's? They cancel. And so now I'm left with just the antiderivative of u du. Oui ou non? Okay. What is said antiderivative? Right. Okay, so or do we buy that? Right, that's just the power rule. And then what was u? Yeah. Okay, would you have guessed that from the get-go? No, but do you buy that it is this now? Okay, how do I check to make sure that I'm not full of it here? Yeah, if I take the derivative of that expression, then I should get what I started with. So let's do that. Okay, so this will be check the derivative of 1/2 natural log of x squared is 1/2 times 2 times natural log of x to the first times the derivative of natural log of x by the chain rule. What happens to the 2's? And so we're just left with this, which is the thing we started with. Okay. Right. So there you go. Okay. Question, preguntas, fragen. Okay. Um, so yeah, if you pick the wrong U, it won't work out so cleanly. Okay. The other thing, though, is that the whole point of this is to reduce a nasty looking thing to something whose antiderivative you just know. Okay. So it's essentially we want to take something from nasty to an antiderivative that we've memorized, okay, by knowing the basic derivative rules. Right? So if we know all the basic ones, then we should be good. Okay. Right. And so there's sort of two other situations related to this that I want to show or that we need to deal with. Okay. The first is that all of the problems that we've done so far are indefinite integrals, meaning there wasn't numbers at the top and the bottom. Okay. And so what do we do if we have a definite integral? Basically, it's not that hard. Okay. But there's a few details that we need to talk through. Okay, so there's that. And then the second thing is some more, these were kind of, Buffalo mild kind of things. Well, let's get some Buffalo medium or Nashville hot going on. Hmm? You guess? Has anybody done the new blazing wings now that they've incorporated ghost pepper into it? Have you had them? Yeah. I think you would remember if you'd had them. Oh, okay. Yeah. Uh, yeah, it is kind of funny how humans do the spicy thing, right? Because why is it that the chili peppers are spicy in the first place? Do you guys know? Yeah, to keep mammals from eating them. Okay. But birds, the capsaicin doesn't do anything to them. Okay. So why is that good from an evolutionary standpoint? Yeah, their seeds get moved because if I'm a mammal, a terrestrial mammal, and I eat a pepper and then it goes through my digestive system and I eliminate the waste, how far away from the original pepper plant is that going to be? Not all that far. Whereas if it's a bird and the bird eliminates the waste that includes hopefully some undigested seeds, that could be really far away, right? So it's better for the pepper plant because it spreads the seeds far and wide. And then humans came along, and we're masochists for some reason. So yeah, we like the pain. Okay, um, good. So let's deal with the definite integral situation, and then we'll look at a spicier example. Okay, so for this, let me just pick a problem we've already done actually. So we just did that, right? And just for sake of demonstration, let me change it to being the definite integral from 1 to 2. Uh, I'm sorry, that's not what I meant to write. I meant to write that. Um, yeah, okay. So let's just say that that's what we had. And the 1 and the 2 I've kind of picked just arbitrarily for sake of demonstration. Although, is it clear that I couldn't have picked 0? Yeah, because x can't be 0 both in the denominator and the numerator, okay? Actually, in Calc 2, you can deal with that situation, but it not shockingly involves limits because this is a calculus class after all. But yeah, okay. So we got that. And we already know what substitution to make, okay? So there are 2 options. The first option is just to blow off the problem and say, I'm just going to ignore that the 1 and the 2 were there at all, okay? And if I ignore that the 1 and the 2 are there, can I do the problem like we did before? Okay, so how do I know that this is equal to that? Because I just did it a minute ago, right? And let's say that we hadn't just did it a minute ago, then this equal, there would have been a lot more work here, okay? So what I'm trying to say is the if you've got a definite integral, you can just pretend it's an indefinite integral, go through, figure out the antiderivative, and then deal with the numbers at the end, right? That totally works, okay? We uno. So I'm not blowing off the numbers entirely. I'm just blowing them off until after I've worried about the antiderivative part. Okay? Because once I've got the antiderivative, all I got to do is plug in the numbers and do the arithmetic. That's it. Okay? Does that make sense? Right? Just to sort of split it into 2 issues. Okay. So that certainly works. Okay. There is one other option that we have though. Okay. And while it's not necessary to do it here, because option 1 exists, what we'll do in option 2, that idea is sometimes useful in other contexts, and so it's worth looking at now. Okay. Um, this one? Oh, well, what's the natural log of 1? 0. Right? And so that term is just poof. Now, how did I get natural log of 2 squared minus natural log of 1 squared with the 1/2? So how did I get from here to here? Yeah. And you are the only person I have ever met that says log natural. What's up with that? It's stuck? Okay. Yeah, I mean, I'm not saying it doesn't make sense. It's just, huh? No, it's an L. If it was an I would have put a tittle on it. Oh, yeah. Yeah. Well, and actually, did you guys know this? So the letter I, the dot on top of it, is called a tittle. Tittle. Yeah. Well, and I mean, I will say, right, I do kind of have a bag full of dongles. So I know it's so horrible, right? Um, yes. Okay. So the other option here is to deal with the numbers as you go. Okay, and so to do that, let's actually go back to what the substitution we made was. Okay, and here we did that. So if u is equal to natural log of x, oops, sorry, I forgot the dx there. The 1 and the 2 are numbers in terms of x. Okay, how do I know that? Because it's blah, blah, blah dx. Okay, so the 1 and the 2 are x numbers, and I want to transform them into their corresponding u numbers. Well, how do I do that? If x equals 1, then what's the corresponding u value? Okay, and how did you get that? Yeah, you just plugged it in for x in my u formula. Okay, and then did the arithmetic. What's the natural log of 1? 0. Okay, and then similarly, if x equals 2, then u is the natural log of 2, and that's just the natural log of 2. There's nothing to do there. Okay, and so our new problem turns into that. Okay, now, do you guys, I have technically skipped a whole bunch of steps here but like last time, when we did the substitution for log x over x, it turned into just u, right, from the previous page. Okay, so this arrow, right, incorporated the stuff that we did 10 minutes ago. Okay, yeah, okay. Okay, and now we can just finish because, well, what's the antiderivative of u? Yeah, 1/2 u squared. And then I'm going from 0 to natural log of 2. Can I plug those two numbers in? And I get, obviously, the same thing that I got before, but a different way. Okay? Does that make sense? Okay, so, like I said, if there are numbers on top and bottom and you need to do a u substitution, you can either keep up with the numbers as you go or blow them off and deal with them at the end. Experience. I know it doesn't help, right? Strictly speaking, you can use either of them anytime. But I think um, so the one advantage to dealing with the numbers as you go is at this stage right here, did we ever substitute that u was equal to natural log of x back in? No. Okay, so the advantage of keeping up with the numbers as you go is that the x's don't go back into it. You just plug in the numbers, right? Because you've already converted them. But you're doing more all at the same time, right? So the advantage of option 1 is you're restricting your attention to just the antiderivative part and then dealing with the arithmetic part later. So you're separating things out and only concentrating on one thing at a time. Okay, yeah, Julius. Oh, well, it'd be minus 1. What happens if I plug 0 into this, right? Yeah, so minus 0. Right, because you subtract. Now, obviously, in the case of 0, it doesn't matter if you subtract or add. But um, what does the fundamental theorem say, right? You've got a definite integral. You find an antiderivative, plug in the top number, plug in the bottom number, and put a minus sign in between, right? Okay, so that's why it's minus. Okay, good? Okay, now, that said, the reason okay, most of the time when I'm doing these, I do option 1, okay? Not exclusively, but most of the time I do. Um, However, option two, um, this idea of transforming the bounds, so what those numbers are, um, is useful in other contexts. Okay. For example, in Calc 2, um, the bounds don't have to just be numbers, they can have letters in them also. And sometimes actually it's useful to think about it in that way. Okay. Um, in fact, in Calc 2, you deal with problems like this, right? Why do one integral when you could do two of them? Yeah. And if this a single integral is area under a curve, then guess what a double integral is? Volume under a surface, a three-dimensional surface. Yeah? You should all take Calc 2. Oh man, it's so much fun. Okay, so, right. All right, so which method do you think guys seem to like better? One or two? One? Okay. And that's fine, right? It doesn't matter which one you go with. You will get the same answer if you, well, yeah, I mean, key word there being if, right? So, okay, good. We, all right, so let's look at maybe a slightly spicier one. And to motivate the question, let me start with this. Do I need any fancy pants techniques to deal with this problem? I claim no. Okay. Why, Patrick? Why don't I need a fancy pants technique? No. Thanks for playing. Can I split this fraction up? Yeah, into x over x, which is just 1, right? And then I can be like, oh, okay, well, that's x, and this would be 5 natural log absolute value of x, and then my plus 8 done. Uh-huh, of course. Okay, so I can do a little bit of algebra to simplify or rewrite the thing that I'm integrating, okay? And I was able to split up that fraction because what I basically just did was common denominators, but in reverse, right? Is that okay? All right, I only changed the question. Nope, doesn't work that way. Sorry, thanks for playing. Yeah, it's not 1 over the thing that we started with. Okay, that's the same thing, right? All right, can I split this fraction up? Jaden's shaking his head. Why, Jaden? Can I not split up this fraction? Yeah, okay, you cannot split up fractions where the sum is in the denominator, right? I mean, I know that 5 out of 4 Americans struggle with fractions, but, um, oh, come on, I gotta get, yeah, thank you, Patrick, thank you. Okay. For bad math dad jokes, yeah. Well, have you guys heard the one about, so my dad, he used to work before he retired for the Transportation Security Administration, right? The people that take away little scissors from grannies at airports. Um, Actually, every now and then they find some really hilarious and weird things. Uh, when they find a loaded gun, that's neither hilarious nor weird. That happens more often than you'd care to know. No, not with grannies, but yeah, they find some weird stuff sometimes. So, um, my dad kind of kept a collection of like strange confiscated items to use in training and just be like. So the weirdest one. and they didn't confiscate these. Let's say that you're X-raying a piece of luggage, okay, and you see a bunch of things that look like bricks. What are you going to think that's in there? Okay, you're going to either think it's cocaine or C4. Okay, but you know the weight, right? Because you had to pick up the bag. Okay, so you'd probably think that it was either C4 or cocaine. Okay, and if they were all like perfectly rectangular, you're probably going to go with C4 because cocaine, nobody wraps their cocaine that neatly. Okay, I mean, I'm told anyway, right? Um, okay, so yeah, you might think it's C4 and call in the bomb squad. So this happened once at the airport, and the bomb squad gets there, and they're like, nope, there's no signs of explosives anyway. So they open it up, and guess what they saw? Nope, not C4. Nope, those would be big ass candy bars. Bricks of cocaine, right? No, they were the blocks of Velveeta cheese. Okay, and it turns out that the density of them is exactly like C4, right? So it looks like it's C4 on an X-ray machine. Now, this begs the question: why would somebody have blocks of Velveeta cheese in their suitcase? No. Okay. Uh, I don't know. Yeah, maybe. I don't know. Well, I probably not because it's not just about how it looks on the X-ray, but like they can do swabs and stuff to detect residue of it, and you can't get rid of the residue, basically. Um, right. So anyway, this begs the question: why would somebody have a suitcase full of Velveeta? Huh? Well, they make mac and cheese or queso, but what about if you're flying to a country where they don't have Velveeta, and your family members are like, "Oh my God, bring Velveeta! It's liquid gold." Yeah. So yeah. Anyway, and so there are certain flights to places in like Latin America, certain parts of Latin America where like when this first happened, like they all freaked out, and then it's like, oh, yep, another thing of Velveeta for the flight to El Salvador or whatever it is, right? So, yeah, or C4, yeah. Well, okay, but let's just say that like if it's the flight going to Bogota, Colombia, the cocaine is probably not going to Colombia. It's probably right. Nobody smuggles cocaine back to where it was manufactured. Yeah, bad product. It's a warranty returned. Yeah. So, okay. Um, right. Okay, so I can't split up this fraction. Okay. But watch this. From cocaine? Because I was going to tell you about the time that my dad had to arrest somebody who was trying to get on an airplane with a compass and a protractor and a straight edge and a calculator because he was trying to board an aircraft with weapons of math instruction. Yeah. Okay. All right. So what I'm going to do here is let me let u equal x plus 5. Du is dx. But if u is equal to x plus 5, what's x? U minus 5. Let me substitute that all in. And I've transformed the problem into that. Nope. Okay, have I put everything in its correct place? Okay, and now I've changed the problem to one where I can break up the fraction. Wow, that's pretty cool. Yeah? Okay, and then it's just what? U minus 5 natural log absolute value of U plus C, and then what was U? Which could I just write it as this? Why? Yeah, because what's 5? 5's a constant, plus C is a constant. What's a constant plus 5? Some constant, right? So I could kind of sweep that under the rug. Either is acceptable. It doesn't really matter. Yeah. Okay, so this was maybe like a buffalo medium kind of substitution. And Wednesday, we'll look at some more exotic ones and also bring your thinking caps and be prepared to get your asses to the board so that you can, yeah. Good? All right. See you guys Wednesday.